Hi guys, it's Miss Lemens again. We're going to go ahead and finish up question number 1, letters B, C, and D. Have that scratch paper out and get ready to follow along with me. So, we've already filled out our BCA table. We did that in the previous video. We have all the information that we now need to calculate B, C, and D to question number 1. So question letter B asks us how many grams of precipitate will be produced in this reaction? Few things here. Precipitate, that is a vocabulary word that we haven't used in a little bit. Remember that a precipitate is a solid that's produced in a double replacement reaction or any chemical reaction. So you want to be careful about which one of these formulas or which one of these substances you choose to use. If you look carefully at the balanced chemical equation, you can see that calcium phosphate is the only substance that has the S symbol after it, which stands for solid. So calcium phosphate is our precipitate. And I'm going to go ahead and write that here so that we don't remember, or so that we do remember. That's our precipitate. Okay, so now we need to calculate the number of grams of precipitate. And we're going to do that by looking at the number of moles of precipitate that were produced, which was 0.298 moles of calcium phosphate. So I'm going to start with what I know. That's 0.298 moles of calcium phosphate. And I need to multiply that by a conversion factor. Now the nice thing here, once you are done using this mole ratio to finish the table, there's really only 2 other conversion factors that you can choose from. We were introduced to these at the beginning of the school year in first semester. We've got the top one here that helps you go from moles to grams or grams to moles, and it utilizes the molar mass from the periodic table. We also have Avogadro's number, which help you go from moles to particles, or particles to moles. And remember, particles can mean molecules, formula units, ions, or atoms. In this case, we're starting with moles and it's asking us to find grams of precipitate, so we're going to use the top conversion factor. If I have moles of Ca3PO4 on the bottom, I'm going to go ahead and put the same on, or on the top, I'm going to put the same on the bottom. And it says in my conversion factor that it's 1 mole of X is equal to the molar mass. So I'm going to fill that in with a 1. The molar mass of Ca3PO42 can be calculated using values from your periodic table and adding them together. So the molar mass for Ca3PO42 is 310.18 grams of Ca3PO42. I know that I've successfully set this up because moles of Ca3PO42 cancels out with moles of calcium phosphate on the bottom, and we're going to be left with grams of calcium phosphate. When I type this into my calculator, the raw number that I get is 92.4334 grams, etc. But we want to round according to sig figs. Sig figs, we started with 3 sig figs, so we want to end with 3 sig figs. Remember, we don't pay attention to conversion factors because they have an unlimited or an infinite number of sig figs. So I'm going to underline my top 3 sig figs, and my final answer here should be 92.4 grams of calcium phosphate. I'll go ahead and rewrite that right here. Okay, so we can now go ahead and calculate letter C. Letter C says that if the final product contains 3.50 liters of aqueous NaNO3, what is the molarity of NaNO3 solution? Okay, so it tells us that our final product has 3.5 liters of this solution, and we need to find the molarity. Again, that's where we are going to use this molarity equation. So that's molarity equals moles of solute over liters of solution. In letter B, we are given the molarity, and using our BCA table, we also have moles of that particular product. So I'm going to start by plugging in the information I know directly into the molarity equation. That should be molarity equals, because we don't have molarity, molarity equals moles of solute, which I get from my BCA table. So we are looking for NaNO3. We produced 1.79 moles of NaNO3, so I'm going to plug that in over here, 1.79 moles. And I'm going to divide that by liters of solution, which has been given to me in this in the question. So that's 3.5 liters of solution. When I divide the numerator and denominator, I get an unrounded answer of 0.511428, etc. Remember, I do want to round according to the rules of sig figs. I started with 3 sig figs. That 0 does count, so I want to end with 3. So my final answer for this particular question is 0.511 molar, and that is NaNO3 sodium nitrate. Okay? So now we can go ahead and calculate letter D. Letter D says if a scientist was using 0.575 molar calcium nitrate instead, what volume in liters would be necessary to produce the same amount of calcium phosphate that you calculated in your BCA table? So we need to find the volume of calcium nitrate. You have to be careful because it's asking you to produce the same amount of calcium phosphate. So all they're saying is that we need to produce the same number of moles of calcium phosphate as if when we started this problem. Do not pay attention to that last bit. It's going to throw you off. What they're saying essentially is you should have the same number of moles of calcium nitrate also because this ratio is the same. Okay? So we're going to be plugging in our information into the molarity equation. I'm going to start with what I have been given to me. So that's 0.575 molar. And that's set equal to the number of moles from my BCA table. So 0.894 moles. And I'm trying to figure out volume, so I'm going to put an X underneath. Now I need to calculate volume, and how you do that to get X by itself, you could go ahead and cross multiply by putting 0.575 over 1. So you'd have 0.894 is equal to 0.575x. You would then divide both sides by 0.575 to get x by itself. Sorry, I know this is kind of small. When you do that, your rounded final answer should be, I guess I'll do it right here, 1.55 liters of calcium nitrate. And this is your final answer for letter C, or letter D.